We are doing related rates. Here's our second example overall and our first example of a cylinder. Let's read the problem, and as we read it, if we can translate things into calculus, we will do so. Water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. Super important, leaking out means we're talking about something that's negative. Just going to put that there for emphasis. If I want to change this to a rate, water is leaking out. You might be thinking, what variable am I going to use for water? W? You're not. At a rate of 3 cubic feet per second. So per second means that the denominator is going to be time, for sure. So the change in time. As far as the top goes, this is a clue. It's cubic feet. Cubic things are measuring volume. So I almost did this wrong just now. Water is leaking out. So the way that I have this written, this means we're adding water. So I need to make sure that I'm careful here, that I am saying this is a negative rate. It's a rookie mistake to not make that negative. Hopefully that never happens to you. If the radius of the tank is 4 feet, so you know what, I should write that down. I'm going to draw a cylinder. You little, come on fella, it's supposed to turn into an arc, but there we go. So this radius here is 4 feet. I'll write that down over here as well. Well, on the steps that I gave you for the previous problem, step 3 was identify, if any, which of the variables in the problem remain constant. So I'll just write that down now, that the radius is always 4. Continuing reading the problem, at what rate is the depth of the water changing at any instant during the leak? So as far as depth goes, I'm going to refer to depth as the height of the water. Step 1 was to convert things into calculus. I guess I didn't convert that last sentence into calculus yet. We want to know at what rate is the depth of the water changing. Whoops, sorry about that. So we want to find the change in depth, which I'm going to call height, with respect to time. It says at any instant, so I don't need to evaluate at a certain thing. So that's what we're trying to get after. I guess I don't need an equal sign there. Highlighting this with the same color that I translated it from. Step 2 was to define any variables that we have. So just looking at, I got volume, I got time, I got height, I got time again. So V is volume. We're told that was measuring in cubic feet. H is height. I don't see this in anything here, but it mentioned that the radius was 4 feet. That was here. Probably should have put an R equals there. So R is radius. We're assuming that the height and the radius are the same units, which are in feet. And then finally, T is time. It mentions seconds in the problem, so the units are seconds. Step 4, if it's a multivariable function, we haven't even written the function down yet, so I should probably write the function, which is step 5. This mentions volume. Volume has a height. It also has a radius in it. The volume of a cylinder or any prism, any rectangular That's not rectangular. Any prism, any right prism, I should say. The volume is always the area of the base times the height. I would memorize that versus trying to memorize a bunch of different formulas. Well, the area of the base of a cylinder is a circle. Area of a circle is pi r squared. And then the height of the circle we defined as being h. Now, before we get into step 6, which is differentiating both sides with respect to time, we wrote in step 5 on the previous page, right here, substitute any value that represents a variable that is a constant throughout the problem. We want to do that now. So for example, in this problem, we are told the radius is always 4. Always. So before we take the derivative, it is imperative that we change this so that it's 4 squared. How much easier does that make the problem? A bunch easier. Because now we only have the equation in one variable. If the equation's in one variable, it is much easier than if it's not in one variable. Step 6, differentiate both sides with respect to time. The left side, the derivative of v with respect to time is dv over dt. The right side, 16 pi is the coefficient, h is the variable. So the derivative is going to be the coefficient. Subtract 1 from the exponent of h, it's h to the 0, which is 1. And then h is a different variable than this denominator. So then we multiply this by dh over dt. Let's refer back to the question. We're supposed to find dh over dt. That's this fellow right here. So the only variable that we have, there's no variable here, is this right here, and we're told what that's equivalent to. So step 7, substitute anything in you can substitute. We're replacing the change in volume with respect to time with a -3. To get this by itself, we divide both sides by 16 pi. And we have to include our units in this. So the change in height with respect to time is -3 feet per 16 pi seconds. If you wanted to convert that to a decimal, so that would give you a better idea of what that means numerically, go for it. AP Calculus test does not require us to do that. So there's our first problem with cylinders. Also our first problem in which one of the variables truly wasn't a variable. It was a constant. Radius was always 4. When that happens, plug it in before you differentiate. Only if it's a constant, the entire problem. Tune in to the next video and we will do an example of related rates and a sphere.